Noise. In procedural generation, we want some kind of randomness that still has some structure to it. This is where noise comes in. So one very simple way to create this is value noise. So it's a very simple type of noise, and you'll see how we can create this kind of a structure that still looks relatively random. So it relies on setting random values and interpolating between them. So let's define some kind of a grid, and let's say that for integer coordinates we set some random values for them. So we have some random values here, it's something like 0.7, 0.4, completely random. And now what we do is that we interpolate between those values. So we create this kind of a structure that has kind of random heights at specific locations. In 2D, it's gonna look like this. So we have some random values, here it's gray, here it's black, here it's more white, so more higher number. And we do bilinear interpolation in 2D to find the values in between them, resulting in this kind of a random looking structure. Now you can of course manipulate this structure, pass it through some other mathematical functions and be very creative with this. For example, you could create something like this. So this is purely created from value noise with just some interesting tricks. Now one thing you can also do is you can kind of sample this noise from different levels and then combine those results. And we can look at a bit larger example in Scikit-learn as well. So we have some value noise at this zoom level, at this zoom level. So we zoom in, zoom in, zoom in. So this is like a very low granularity version, and here is a very high granularity zoomed in version. And if we sum those together, we can create this kind of a cloudy or fog-like texture. And of course you can manipulate like how much you want this layer, how much you want some other layer, and you can kind of create all sorts of interesting visuals with just different layers of this value noise. Now a bit more complicated noise is gradient noise. So this relies not just setting the random values at the integer coordinates, but random gradients. So instead of just one value, we have a random gradient. Right now in this example, we have created normalized gradients. So these are all from unit spheres. They all have length 1, but their direction is random. The most popular gradient noise is Berlin noise. It's created by Ken Berlin in the 80s. So let's see what do we do with these random gradients to get the actual noise values. We have a sample coordinate. So we're sampling our, let's say, 2D space from some specific coordinate, and it lies between two of those random gradients. So we're gonna need two vectors. One vector is the location vector from one of these gradients to our location, and another is from the other gradient to this location. And then we do scalar projection of these location vectors onto the gradients. Mathematically, this is just a dot product because our gradient vectors are normalized. So we just take the dot product of this t1 onto g1, and we end up with this value p1. And the same thing for the other gradient. Now to get the noise value, we interpolate between the values we got from those scalar projections. So we interpolate between p1 and p2 based on the distance, let's call it t, from the left gradient. So we can define this t as just the length of t1. And this will be the result. So what kind of happens here is that if our point moves towards one of the gradients, its contribution gets larger, but the scalar projection value gets smaller. And you can see like along these different segments here, we're getting these different values. Now it might have already been obvious from the previous picture, but you can see that linear interpolation, or in this case bilinear interpolation, is not really good, because we see these edges or these corners here, and these corners are exactly the corners that we saw down here as well. So what happens is that we actually have this parabola along between all of these gradients, and then, well, they do not match, and the entire surface is not going to be C1. So this doesn't look very good. And we can kind of investigate why this happens in more detail. So we have the values p1 and p2, which are the scalar projections. We have this variable t, and we do this linear interpolation between p1 and p2. So let's write out how did we calculate p1 and p2. Well, currently we just took the dot products. So it's gonna be the length of t1 times the length of the gradient times the cosine of the angle between them. And similarly here, for p2 we're just using t2, gradient 2, and the angle between those two. Now, of course, the gradient's length is 1, and why I've wrote this out here is because it becomes important a bit later. So for completeness, I just wrote it out here, but remember that right now our gradient's length is 1, so this just goes to 1 and kind of cancels out. Now, of course, the length of t1 is just gonna be t, and well, the length of t2 is gonna be 1 minus t, because that's the vector from the other gradient to our location. Now let's look at this cosine. So we don't know what this angle is, but it's kind of constant. So depending on the gradient value, even though our t is going to change, the angle between them still stays the same. So we're gonna just write this as c1, and this other cosine of this angle, we're gonna write this as c2. And now to simplify this, we end up with t minus t squared times c1 plus c2. And well, let's just create another variable c3, which is gonna be c1 plus c2. So we get c3 times t minus c3 times t squared. So this is our noise value. Now we can find the derivative of it. So the derivative is just gonna be c3, t will cancel out, and then 2 times c3 times t, because we had t squared here, so 2 is going to come to the front, and only t will be left here. So the derivative is c3 minus 2 times c3 times t. And we can find out what happens at t equals 0 and t equals 1. Well, at t equals 0, all we have here is c3, and when t equals 1, then we will get minus c3. And now this is the problem. So our c3 was the cosine of one angle plus the cosine of the other angle. For example, here, the derivative on the right here is going to be minus c3. So it's going to be minus cosine of alpha 1, this angle here, and minus cosine of alpha 2, this angle here. So it's dependent on both of these angles between those gradients. Now on the other side here, we have the derivative at 0. So the derivative at 0 was just c3, just cosine of one angle plus the cosine of another angle. But here we're using the angles between the gradient and these direction vectors. So these angles beta here. So the derivative for this segment of noise at the beginning here is going to be cosine beta 1 plus cosine beta 2. And generally speaking, these two will not equal. You can of course create such angles here that they will equal, but generally if they're random gradients, they're not going to equal. And that's why we're going to see this corner here, because the derivative is gonna be discontinuous. It's gonna have a sudden jump from this minus cosine alpha 1 minus cosine alpha 2 when approaching from here to cosine beta 1 plus cosine beta 2 when continuing from here or when approaching from here. Now there is a way to create this smooth surface here, and the way is to change this t through this polynomial. So let's call it th, and th is going to equal 3 times t squared minus 2 times 3 cubed. This is also called the Hermite interpolation, and in GLSL shader code there's a function smoothStep that actually implements this polynomial. And now we're going to use this th as our t when interpolating between these p1 and p2 values. So let's see what happens with our new th. So our noise value is going to be 1 minus th times p1 plus th times p2. Just like we had before, except now we are using this th instead of just t. Previously we derived that this noise value can be represented as this equation. So p1 was just a dot product between the distance vector and the gradient. The gradient's length was 1, the distance vector length was t or 1 minus t, and here it's important that we use t because the length of this distance vector is 1 minus t and t, not th, and the cosine of the angle, so our cosines c1 and c2. So let's write out our th as this polynomial that we had, and this is also multiplied with t, so the factor here is going to be t minus 3 times t cubed plus 2 times t to the fourth, and similarly we can write it out here. So it's gonna be th times this 1 minus t, and this will be the result. And now we can also find the derivative. So if we take the derivative of these components here, we get these factors. And now let's see again what the derivative of our noise is at t equals 0 and t equals 1. If we set t as 0, these terms will be 0, here we will have 1 times c1, and if we put 0 here, well, all of these terms have t in them, so all of this becomes 0. So we're only left with C1. Now if we put 1 here, you can see that this will become -9, this will become 8, and this is 1. So all of this will become 0. And on the right here, you see that we have 6 plus 8, so this is going to be 14, and then -15. So all of this will be -1. So the derivative of our noise at t equals 1 is gonna be minus C2. And now let's look again what happens at this knot. So if you approach from the left here, we're going to have the derivative minus cosine alpha 2, because it was minus C2. So it's only dependent on this angle here. But if we approach from the right here, then we get the derivative at 0, and the derivative at 0 for this segment will be cosine beta 1. So this angle here, the cosine of it, but we can make it minus cosine if we take 180 degrees minus beta 1. That will result in minus cosine, and well, 180 degrees minus beta 1, that is just going to be alpha 2 that we had in the previous segment. Thus, we can mathematically see that the derivative of this segment at the starting point is exactly the same, minus cosine alpha 2, that is at the end of the previous segment. And thus we have this C1 surface. And in 2D, well, it's gonna look like this, and this is what is usually considered Berlin noise. We have these random gradients, and we do this Hermite interpolation on the scalar projections. And we can actually improve this. So if instead the Hermite polynomial that we used before, we use this fifth order polynomial, then we can create a surface that is also C2 smooth. And you can easily check this if you find the second derivative using this fifth order polynomial, just like we found the first derivative with the Hermite polynomial. If you do that, you will find out that the second derivative will always be 0 at the knots. Thus the value at the end of the previous segment and the beginning of the current segment will be the same, resulting in a C2 smooth surface. It may depend on your use case if you actually want this C2 smooth surface and use this higher order polynomial and do more calculations, or if you're happy with the Hermite interpolation and this kind of noise. Now there is this interesting question, like what is the value range of Berlin noise? So it can be reasoned that the maximum value is achieved when we take the sample exactly between the random gradients. So exactly in the middle here. You might have noticed that the value of Berlin noise at exactly these points where we have the random gradients, that's gonna be 0. Because the location vector itself is gonna be 0, so the scalar projection also has the value 0. So it can only have the larger values inside this square. And the only case where it can achieve the maximum is when all the gradients are pointing towards it. So all of these gradients say that the values increase to these directions, thus the middle value will be the maximum. So let's look at what happens in this situation. So we have our direction vector t and our gradient vector over here, and we can actually just look at one case, because all of these cases will result in the same value, because the gradients are all pointing towards the middle here, and our sample point is also in the middle, so we're taking basically 1/4 of the scalar projection onto one gradient, 1/4 into another gradient, and so on, but they will all have the same value. So it's just going to be 1/4 x plus 1/4 x plus 1/4 x plus 1/4 x, well that's just going to be x. So we can just look what value do we get from this one scalar projection, and that will be the entire value because the other scalar projections will give exactly the same value. Now we had this dot product here, and if our gradient is normalized, the dot product will give us just the length of the distance vector d. So basically it will just give us the length from this corner to the middle of our square. The angle between d and the gradient is gonna be 0, so the cosine of 0 is going to be 1. So thus in the dot product, all we're left with is the length of t. The length of t is half of this cell's diagonal. Thus, depending on the dimensionality of your noise, you will get different lengths there. If you're just dealing with 1D noise, well then this length is just going to be 1/2. If it's 2D noise, well half of this diagonal is half of square root 2. In 3D noise, you have half of square root 3. And you can imagine it like this. So with 2D noise, we are basically just generating a picture, a flat image of the noise. And with 3D noise, we are filling a volume with the noise. And then you can imagine what happens in 4D and 5D and so on. And there are uses for 4D and 5D noise as well. So with normalized random gradients, the maximum value of Berlin noise is going to be square root of the dimensionality of our noise space divided by 2, because this is going to be the length of the diagonal of that cell, and well, we are taking half of it because our sample point is in the middle. Of course, the range is going to be from minus that value to plus that value. If all of the gradients are pointing away from that middle point, then it's going to be the minimum value, and if they're all pointing towards it, it's gonna be the maximum value. However, there is a catch. So we assumed that our gradients are of unit length, so the dot product only gives us the length of t. But if our gradients do not have length 1, then their length is also going to get multiplied into the noise value. So it will no longer be this pure scalar projection, but it will be multiplied with whatever the length of the gradient is. And in different implementations of Berlin noise, this can be different. It can be lower than 1, it can be larger than 1, they could be square root of 2 and so on. So it depends on how you're generating those gradients and what length gradients you actually want. But with this knowledge, we can calculate what is our maximum noise value from the maximum gradient length. So if our maximum gradient length is 1, then in 2D, our maximum noise value is just square root of 2 divided by 2, just like we saw before. But if our gradients have the length square root of 2, then the square root of 2's in 2D cancel out, and then the maximum noise value will be 1. However, if we have 3D noise, then with different gradient lengths, 1, square root of 2 or square root of 3, we are getting different numbers here. So when you're looking to normalize your Berlin noise into the range from, let's say, 0 to 1 or minus 1 to 1, then you should first find out what is going to be your gradient length, and from that you can calculate what is the maximum noise value, and then you can scale it accordingly. It turns out that with your usual noise, you don't actually see these minimum and maximum values very often. Your gradients are going to be random, and the chance that all of them are pointing towards the middle of a cell so that you would get this maximum value there, this is going to be very low. So I made this manufactured extreme case to test this. So here we have these gradients that are all pointing in the middle, and in the middle we achieve this full white value. And on the right I have 3D noise, and I'm just taking a slice from this 3D noise and animating it to show it like on a 2D picture. So here what happens is that we get this white value in the middle of this 3D cell. We mentioned this gradient vector generation. So different code examples from online do it a bit differently. Well, one very simple way is to just create gradients from this minus 1 to 1 square. So you need, let's say, 2D gradients. You take a random value from minus 1 to 1 as the x-coordinate, a random value from minus 1 to 1 as the y-coordinate, which basically just gives you all the points inside this minus 1 to 1 square, and well, your gradients will be like this. This will give you this kind of a noise, and down here is a histogram of the values of that noise. And these are scaled according to the square root of 2 gradient vector length, because the most longest gradient vector you can have is to the corner, and well, that has the length square root of 2. But there are two issues with this. First of all, you are getting more random gradients towards the diagonals. So you might even be able to see that there's a bit more diagonal tendencies in this noise, because not all of these directions have the uniform probability. The ones on the diagonal, they have more probability because there are more points along this diagonal. The same issue is that you're getting less points over here. And why is this a problem? It's because our largest gradient length is square root of 2. So we're scaling by square root of 2. But not that many of these gradient vectors actually reach the length larger than, let's say, maybe 1. So scaling by square root of 2 scales the noise a bit too much. And this is what you can see in the histogram. So we have very little of these darker tones and very little of these brighter tones. And a lot of tones in the middle here. Because while the maximum length of a gradient here is square root of 2, the one that goes to the corner, a lot of them are a lot less. So when possible, try not to code your Berlin noise gradient generation like that, because these gradient vector directions are not actually uniformly distributed. Instead, what you can do is generate those gradient vectors from a disk surface. So let's take a disk and then generate a random points on that disk, and each of those can be your random gradient vector. And you can see that this gives us a bit better noise. The scaling is better and the directions are actually all uniform. But then we can think like, do we really want those gradient vectors to be also smaller than some fixed value? Because if we get a lot of those smaller gradient vectors, there isn't going to be a lot of change in the noise. So perhaps we want our changes in the noise to be more pronounced. So we can instead generate gradient vectors from a circle with radius square root of 2. So all of these vectors have the length square root of 2, but they're sampled from the circle, the perimeter of this disk. And you can see the noise becomes a lot more deeper and the histogram a bit wider. So here even some very bright values exist. And well, this was the extreme case I tried before. So here I have pointed all of these gradient vectors in the middle of these cells here, and the noise achieves the maximum value in the center points. And we can see that now we do achieve complete white values and complete black values. We can also see that there isn't any clamping, so there isn't like a peak at endpoints. If we would see a pronounced peak here, that would mean that there might have been a lot lower values than 0, or a lot higher values than 1, and all of these were clamped to 0 and 1. So right now we don't see peaks at the end of this histogram, so it should be correct. And here's another interesting gradient vector generation you can do. You could pick a random gradient vector from the gradient vectors that go into the corners of a square. Now this will give you a lot of these diagonal shapes because, well, all of these gradient vectors are diagonal. But it's perhaps an interesting pattern that you were looking for. Now with noise, you should always be creative. So if you take your regular Berlin noise, gradient noise, even value noise, you can apply lots of different math functions on the noise. And very simple thing that will create you something called pillow noise is just taking the absolute value from Berlin noise. It will create you these kind of stringy shapes, like there's this one big thread going all across this picture. And if you take 1 minus pillow noise, you get something called ridged noise. And you can also add animation to the noise. If you rotate the gradients in time, then you can create something called flow noise. So this noise kind of looks like there is this flow going on, like some kind of a water or liquid is flowing in some specific, like quite arbitrary direction here. And you can also create 3D noise. Like the example we saw before, you can create 3D noise and then sample a slice from that noise or do something else interesting with it. Other things you can do with noise is, for example, you can use it to create this landscape on, let's say, a planet. So you take some noise, you mix together different layers of noise, just like we did before, and then you can color your planet surface, let's say, according to the height of the noise or the value of the noise. So if your noise has, let's say, larger values than 0.7, then that's going to be land mass, and everything below 0.7 is going to be water. And maybe this land mass, then let's say everything above 0.8 is going to be more lighter green, and maybe everything above 0.9 is going to be this higher, let's say, mountain peaks. Maybe you put some white color there to represent snow, and so on. Of course, you can use the same noise to also displace the vertices of your sphere. So this would actually create you this 3D shape. So here we can see there is this big mountain here, and there is this snowy peak, and then the places where the noise value is low, you might have water. And then you could also calculate the normal vectors and light up this very wobbly planet. Notable examples from movies and games include the Tron movie. So in 1982, Tron, the original Tron movie, came out, and Ken Berlin actually worked on this. It's rumored that he invented the Berlin noise specifically for this movie. And well, on this character we can see that there is this very noisy outline, and even the surface here is some kind of a noise that's very fastly rotating. This is probably the noise that Ken Berlin created for this movie that became known as Berlin noise. Other examples can include sci-fi movies and TV shows. For example, here we have this Babylon 5 from 93 to 98, so quite an old TV show, but they had this hyperspace there. So the background was this noise, animated noise, this red, very mysterious and scary background. So this hyperspace was like this very scary place. Or here we have this kind of a portal, so that the noise kind of swirling, representing this portal that goes into space. Also, so this is one of my favorite video games from 1997, Little Big Adventure 2. So there was this door on this face here, and this very mysterious face had these eyes, and on the eyes there was this animated noise. This was this mysterious school of magic, very very scary place perhaps. You had to go through like a graveyard to get there, and there was this magical face with these magical eyes, and this animated noise kind of presented this feeling there. So from this video you should understand value noise, very simple noise. You just take random values and interpolate. How to create this noise and what are its shortcomings. And you also learned this technique of layering different layers of noise. Of course you can do the same technique with gradient noise as well, even though we just saw it with value noise. But if you layer it, you can create these clouds and different fog effects that look relatively random. Then we learned, well, gradient noise, namely Berlin noise. You now know how Berlin noise is created. You know the interpolation differences. So if you're using the linear interpolation or Hermite or fifth order interpolation, what exactly happens with the noise? Is it going to be only C0, C1 or C2? We also saw its value range. So how do you calculate the value range from the lengths of the gradient vectors? And we also saw several examples of gradient vector generation. Are you generating those gradient vectors from a sphere, a disk, a square? So it's up to you, but you have to make sure what's the distribution of these gradient vectors and what are their lengths in order to normalize the noise into a correct value range. Then we also saw that with noise you should be quite creative, add mathematical functions to it, try different things. It's all up to you. It's a very creative process, and we saw different example uses from some video games and movies.